dear learners, welcome back. We will discussing here how the cycloaddition reaction takes place and how the molecular orbital involvement takes place during the cycloaddition reactions, and on the basis of number of p orbital involvement, how can we classify cycloaddition reactions. We have seen there how 2+2 cycloaddition reactions take place and how the HOMO and LUMO of both the reactant involved during the cycloaddition reactions. Learner, we will see involvement of HOMO and LUMO if the cycloaddition is thermally induced and if the system is 4n system. Learners, in thermal conditions, if the system having 2 pi electrons, 4 pi electrons or 8 pi electrons, in thermal conditions we can say here the ground states have 2 electrons. So, ethene having 2 pi electrons, so ground state having 2 electrons. So, psi 1 having 2 electrons, that is its HOMO. Similarly, the anti-bonding orbitals, that is a LUMO, is empty over here. So, learners, in the previous lecture we have discussed more conservation of molecular orbital symmetry approach. So, conservation of molecular symmetry is that the number of atomic orbitals are taking part in the reactions, the bonding number of molecular bonding orbitals should be same, and if 4 atomic orbitals are involving in the reaction, we get 4 molecular bonding orbitals, and out of 4, half are bonding and half are anti-bonding. So, in the thermal condition, the psi having HOMO is in ground state having 2 pi electrons. So, we will see how the reaction takes place. So, HOMO and LUMO of the both the reactants, both are having LUMO are of that ethene having opposite spin, but HOMO having in p and p orbitals we can see here same lobe or same sign. So, if you will see the interaction, mode of interaction or stereochemistry, if you will see the 1 orbitals of the each HOMO and LUMO interact, we get a superficial attack. But if you will see the other side, the lobes are different. One is positive, another is negative. So, I have represented that lobes in colors, pink colored. So, colors is sign, colors means the interaction is the same, but here we are getting in other side there is a no interactions. So, HOMO and LUMO, one interaction is superficial, another side is no interaction takes place. So, wave functions are not matching, we called it symmetry forbidden. So, in that case, in thermal condition, always remember learners, in thermal condition superficial attack or interaction is not allowed for smaller size of system or smaller size of molecules. Pi 2s plus pi 2s represent 2 pi electrons of one reactant and 2 pi electrons of other reactant, and S represent the superficial. So, in thermal condition, in 2+2 cycloaddition reactions, S plus S or superficial interaction is forbidden, but S plus A, S is superficial and A is antarofficial, geometrically favored when the system is having a bigger size. Now, reaction is forbidden in 2 pi plus 2 pi cycloaddition reactions. We can see here 2 ethene molecules, that is the thermal conditions. Learners, ground state of HOMO and LUMO combination of 2+2 system does not allow S plus S addition, or because on heating, it is very important, because on heating, because this is thermally induced reactions, we are discussing here thermally induced 2+2 cycloaddition reaction, because on heating the pi electrons of ethene are not promoted as the faces of orbitals are incorrect or the sign are different. This concerted reaction is called symmetry forbidden. So, in 2+2 thermal cyclization, the superficial pathway is forbidden. Important point: when approach of molecular planes is perpendicular or orthogonal, one surface of pi orbital of one reactant react with both the surface of other reactant. We can see this example. This is 2+2 cycloaddition reactions. One of the interaction is superficial and other of the interaction is interficial. So, in that case, when the reactant is bigger in size, the twisting about its original pi bonds takes place, and in that case the system bear the strain, and we can call it symmetry allowed. So, in that cases, when there is a bigger molecules or bigger involvement of pi electrons system in the reactions, it is called symmetry allowed interactions. So, for 2 pi plus 2 pi system, geometrically interaction is very difficult. It is a very rare. Interficial attacks is very rare in thermal condition in 2 pi plus 2 pi cycloaddition reactions. Now, what happen when the reaction is photochemically induced? So, we are again talking about the 2+2 cycloaddition reactions. Learners, photochemically it means when the reactant absorb photon, what happen? The one electron which was present in the ground state jump to the higher state. So, in that case you can see here psi 1 having 1 electrons. Similarly, after excitation, the 1 electrons jumps to the LUMO, that is the anti-bonding orbitals, and that LUMO is called new HOMO, that is psi 2. So, the psi 2 and psi 1 both are having 1 electrons, and both that orbitals having opposite spin, psi 2 having opposite spin. Now, we will see how the interaction takes place, how the 2+2 cycloaddition reaction takes place when the reaction is photochemically allowed. So, learner, we can say here both the LUMO and HOMO of both the reactant having opposite spin. So, you can see interaction is allowed. You can see in the structure both are having same phase. So, in that case interaction is possible. Same phase, this is called superficially interaction again. So, it is geometrically feasible, and this is reaction is allowed. Superficial reaction is allowed. 2+2 cycloaddition superficial interaction is allowed in case of photochemical reactions. So, this is, learner, very important. You must know how the molecular orbital, how the HOMO and LUMO of both the reactant involved during the reaction. What is the signing of that lobes which takes part in the reactions? So, HOMO of excited state have same symmetry as the LUMO of ground state. So, 2+2 cycloaddition photochemical reaction superficial interaction is allowed, but 2+2 cycloaddition thermal condition, the reaction is forbidden. So, reaction of cis or trans 2-butene in 2+2 cycloaddition reactions, in that case intramolecular cyclization takes place and we get a cage like structures. So, when two molecules of cis 2-butene react with each other, two molecules of here 2 electrons of one cis butene, 2 electrons of other 2 cis butenes involved in the reactions, we get a 2 different products. So, this is a intramolecular cycloaddition reaction. Similarly, if 2 trans butene react, that is a photochemical condition. So, again we get a 2 different products. So, we can see here the stereochemistry also during the reaction takes place. So, 2 possible products can formed in concerted pathway when the 2 molecules of cis or 2 molecules of trans butene came together in 2 different ways. Learners, thermal cycloaddition is allowed only when the reaction is interfacial of the reactants. Now what is the condition? We can say in the example ketene. Ketene is a very important example of the cycloaddition reaction, where 2 plus 2 cycloaddition reaction, interfacial reaction takes place, interfacial mode of interaction is interfacial, and the criteria of the reaction is thermal. So ketene cycloaddition we will see here. Ketene is a very important class of organic compound. We can prepare a lot of organic compounds using the ketene. So in ketene you can see C double bond C double bond O. So when this ketene react with ethene, we get a superficial and interfacial allowed reactions. So this is very important example, thermal condition 2 plus 2 where interfacial reaction is allowed. Similarly, this is another example of ketene where 2 plus 2 cycloaddition reaction takes place and the mode of interaction is interfacials. Another example we are looking here, this is another ketene, and this ketene react with ethene and 2 plus 2 cycloaddition reaction takes place. And this is another very important example where HOMO of the one reactant react with LUMO of the other reactant at thermal condition, and it allow the superficial of one lobe of the p orbital and interfacial of other lobe of the p orbital. So these are the very important example where we can see 2 plus 2 cycloaddition reaction when the reaction is thermally allowed. So in ketene, linear geometry of sp hybridized carbon leads to minimum repulsion in interfacial transition state. That's why we can see 2 plus 2 interfacial attraction or bonding interaction, because there is a sp2 hybridized in a ketene. Due to that sp2 hybridization, there is a minimum repulsion. So this is the example we can say here, it is a geometrically allowed. So I have represented here the molecular orbital structure, overlapping takes place, and geometrically favored reaction is we can see over here because there is no steric hindrance. So 2 pi electrons or 2 p orbitals superficial and 2 p orbitals interfacial reaction takes place here. This is another important reaction. This is here also ketenes. So in all reactions we can see superficial or interfacial mode of interaction in 2 plus 2 cycloaddition reaction when the reaction is thermally allowed. Learners, the more bulkier group on the ketene will tend to end up on more sterically hindered face of cyclobutane ring. So 2 plus 2 cycloaddition reactions, always remember thermal condition, it is possible when there is a bigger ring. So superficial plus interfacially geometrically allowed only in bigger molecules. Otherwise 2 plus 2 thermal condition superficial reaction or mode of interaction is forbidden, but on photochemical condition 2 plus 2 cycloaddition superficial interaction is allowed. Learners, we will see Woodward-Hoffmann reactions or stereochemistry of 4 plus 2 cycloaddition reactions. 4 plus 2 cycloaddition reaction is also called Diels-Alder reactions. So we will see how the mode of interaction takes place, how HOMO and LUMO interact in 4 plus 2 cycloaddition reactions. So we will see in thermal conditions. So as I told you in the previous class, in 4 plus 2 cycloaddition reaction, 4 electrons of the one reactant and 2 electrons of the other reactant involved in during the reaction. So we will see here, because there are 4 electrons in thermal conditions, Psi1 having 2 electrons and Cy2 having also 2 electrons. So these are the bonding electrons. Bonding electrons are having always lowest in energy, lower in energy. So here ground state Cy2 having 2 electrons. So ground state of HOMO is Cy2, unsymmetric, allowed 4n system. So we will see if this is conjugated diene react with enophile, we get a cyclic product. So HOMO of diene react with LUMO of enophile, we get a conjugated product. We will see now. You will see here, it's a very important example. What is the stereochemistry behind the? So learners, as I told you, during the interaction, we will use only last loop. So Cy2, which is the ground state, which is the HOMO of 1,4-butadiene having opposite spin. Similarly, LUMO of ground state of ethene having opposite spin. So are you looking here? Can you see here the interaction? Which type of interaction takes place here? Yes, lobes are symmetrically allowed. So if both the lobes are of both HOMO and LUMO of p orbitals are allowed, we get a superficial interactions. So you can see here 4 electrons of the 1 butadiene interact with superficially. Similarly, 2 electrons of the ethene interact with interofficial. So remember learners, 4 plus 4 to cycloaddition thermally allowed superficially, while you have seen here 2 plus 2 cycloaddition, superficial attack is not allowed, superficial interaction is not allowed if the molecules are in reactant are in smaller size. So another example you can see here how the HOMO and LUMO interaction between Cy2 LUMO of ethylene and Cy2 HOMO of 1,3-butadiene is feasible because of small energy gap. So both the example we have seen here superficial interactions, but if you will see here learners, what about the Cy1 and Cy3? Is Cy1 and Cy3 interaction is allowed? No, Cy1 and Cy3 p orbitals, you will see here this distance is large energy gap. So Cy1 and Cy3 cannot superficially allowed. So we will see now 4 plus 2 cycloaddition photochemical reactions. If 4 plus 2 cycloaddition is photochemically induced, so we will see the energy level over here. When this 1,4-butadiene absorb photon from the light, what happen? Excitation takes place. 1 electron from the Cy2 jumps to the Cy3. So you can see here HOMO, which is the Cy2 having 1 electron. Similarly, LUMO, which is Cy3, is also having 1 electron. So after absorption, excitation, HOMO and LUMO having 1 electron each. So HOMO of butadiene and LUMO of ethene both have different symmetries in case of photochemical reactions. So we will see what is the mode of interactions allowed when the reaction is passed through photochemically. So allow interaction interofficially photochemically. We will see here LUMO of ethene, that is the Cy2, and HOMO of butadiene. You can see here interaction is allowed. No, 4 plus 2 photochemically interfacial interaction is not allowed because the symmetry is forbidden. Due to symmetry forbidden, the reaction is not allowed. Interofficial cycloaddition photochemical reaction is not allowed. So learners, this is Woodward-Hoffmann rule for cycloaddition reactions. So please, you must remember this Woodward-Hoffmann rule cycloaddition tables, and I have represented here number of pi bond of both the reactant. This is the cycloaddition reactions. So if the system is 4n, or we can say the number of pi bonds 4, 8, 12, then if the reaction is induced thermally, the interaction of bonding superficially and interficially. In that case, if there is a bigger size. If there is a bigger size, the interfacial interaction or bonding is allowed. But the smaller size, if there is a smaller size, 2+2 cycloaddition, especially in 2+2 cycloaddition, interfacial addition or interfacial interaction is not allowed. Similarly, if the reaction is photochemically induced and the number of pi bond and the system is 4n system, superficially and superficial plus superficial interaction is allowed. So, 4n system in photochemical condition, superficial interaction is allowed, superficial bonding is allowed. Similarly, if the system is 4n plus pi 2, 4n plus 2 pi system, it means that system having 4, 6, 10, 14 electrons or odd number of pi bonds. If the both of the reactant have odd number of pi bond, in that case what is the reaction conditions? If the reaction condition is thermal, if the reaction is this cycloaddition reaction is passed through the thermally or induced thermally, in that case superficial interaction is allowed, but photochemically, superficially and interfacial interaction is not allowed. Superficial, one reactant, p orbital of one reactant can be interact superficially and other can be interfacial if the size is bigger. So, symmetry allowed. Interfacial bond formation can occurs only in larger rings. So, learners, for cyclic addition, this is a very important condition. For cycloaddition reactions, the dienes should have S symmetry. The dienophile and diene which are reacting in the cycloaddition reactions, 4+2 cycloaddition reactions, that should be in S geometry. So, S cis or S trans, we can say here this is 1,4 butadiene having 4 pi electrons. So, for the 4+2 cycloaddition reaction, that should be S cis geometry, because if there is a S trans symmetry, electrons are far away from each other and not participate in the reactions. So, learners, we will see here cycloaddition reactions are very stereospecific reactions. Number of according to the number of reactants which are taking part in the reaction, we get a different stereoisomers. We can say here two reactant, what in one reactant H and pH are trans to each other. React with ene, we get a two stereoisomers. In that stereoisomers, both pH are trans, that is are above of the plane, and H is also trans to each other. So, that's why cycloaddition reaction is very stereospecific reactions. In this example, we can say here, during the cycloaddition reactions, the substituent on the same side of the diene or dienophile will not change their stereochemistry. So, here we can see H is cis to double bond in the enophile and COOCH3 during the cycloaddition reaction, that will be remain on the same phase and we will get a cis product. Similarly, if H is trans to each other, we get a trans product. So, we can say we are getting a same plane, all the substituent on the same plane. That's why we called these cycloaddition reactions or 4+2 cycloaddition reaction is stereospecific in nature. This is very important example. You can see here the cis enophile react with dienophile, we get a cis product. Similarly, very important reactions, stereochemistry of the reaction depends upon the diene. So, diene, which type of substituents attached to the diene and where substituents is attached, the stereochemistry depends. In this case, if during the reactions the outer groups are always below of the plane and inner groups should be always above of the plane. So, R, this is a diene, R is inner group and H is outer group. So, we will see in the reactions both R and H, alkyl group or R group are cis to double bond. So, if you see the cycloaddition product, this is a 4+2 cycloaddition product, thermal reactions. So we will see here R and H. R should be inner, this is an inner group, and it will be always remains inner of the plane, below the plane, and one is outer of the plane. So these are very important. So stereo selectivity and stereo specificity depend upon the groups where the substituent attached. This is another example. This H and pH are trans to each other, so we get a product where H is above the plane and pH is below the plane. So learner, this is again very important examples. Cyclodienes are more reactive for Diels-Alder reaction. We have seen the Diels-Alder reaction or 4+2 cycloaddition reaction where the 1,4-butadiene is acyclic, but in case when the diene is cyclic, this is very reactive. So we are looking here as cis configuration. This cyclic diene react with 2 pi electron system, 4+2 cycloaddition reaction takes place, and we get a substituted product. We get a cycloaddition product, 4+2 cycloaddition product. Here we can see here the substituent COOCH3 is cis to the bridge. So cis to the bridge in this case. Similarly, in another case when COOH is trans to the bridge, or we can say towards the concave carbon, I have represented here concave carbon. So substituent is trans, bridged carbon, and towards the concave side of the ring. So in that case, when substituent is S to the bridging carbon atom, it is called exo product, and when trans to the bridging carbon and towards the concave carbon atom, this is called endo product. So learner, exo product is favorable due to less steric hindrance, and exo product is very favorable due to less steric hindrance. Similarly, endo product is less favorable due to steric repulsion. So you have to remember few points while doing the Diels-Alder reactions. In Diels-Alder reactions, when reactant is cyclic, less stable end product is major and thermodynamically stable. It favors the superficial overlap between the orbital of same sign on the dienophile with diene. So no such interaction takes place in exo transition states. So we can see here this is a exo transition states, and presence of electron withdrawing group on diene also favor the Diels-Alder reactions, because due to their effect in raising energy of dienes, HOMO of that reactant make it more complete with dienophile with LUMO. So important point is when electron donating group is present at C2 or C3 carbon atom, product will be 1,4 not 1,3. So this is an example. Here 1,4 product is more favorable. Similarly, when the electron donating group is attached and C1 carbon atom or C4 carbon atom, we will get a product 1,2 and 1,4. So 1,2 is more favorable product. So similarly, this is example of intramolecular Diels-Alder reactions. The reaction takes place within the molecules. One end of the system act as a ene, other end of the system and as a diene. So both diene and ene having within the molecule. So stereochemistry of intramolecular addition reaction depend upon the substituents attached to the diene. So learner, we have discussed types of cycloaddition reactions, stereochemistry of cycloaddition reaction, mode of interactions, how the superficial and interfacial interaction takes place during the reactions. Thank you.